Good morning to all of you. All right, I'll begin today's session. Previous session we were discussing the BJT, the power BJT. We started off by looking at the structure of a power BJT. We found that the N- layer contributed in having a higher voltage rating, voltage blocking capability of the BJT. And then because of the addition of N- drift layer of sufficient thickness, the characteristics, VI characteristics in fact had two distinct regions. One was the quasi-saturation region, the other one was the hard saturation region. The remaining two regions, namely cutoff region and active region, they were quite similar to the classical low power BJT. And as far as the operating principle is concerned, the BJT has to be turned on. That would mean the region, the BJT has to start from the cutoff region, and then there has to be charge carriers so that the device is biased in the active region, followed by the quasi-saturation and finally the hard saturation. So this is the process that has to take place inside the device, because of which there were distinct time intervals. For instance, rise time was 1, rise time 1, rise time 2, fall time 1, fall time 2, etc. So those were the time delays that were present or that were observed in the turn on characteristics of the power BJT. Turn off was exactly similar. Of course, I want you to refer a textbook and then become familiar with the turn off characteristics as well. That will be exactly similar, or in other words, the reverse process of whatever had happened during turn on process. This is what we had come across in the previous session. The next logical device, that is actually the, you can tell that it is the workhorse, or it is the major power device. It is the head of the family of power electronic device. Fine. So the device that we are going to discuss today, that is called as the head of the family of all the power devices, because that was the first power device which was invented in 1957 by General Electric Research Lab. It is called as thyristor. That is the group name, the family, family's name, you can consider that way. Whereas if you want the device specific name, it is called a silicon controlled rectifier, or SCR. We will discuss the important features of SCRs in this session. It will take one more session because that is the main workhorse of that was actually, of course, nowadays nobody is, I wouldn't say nobody, nowadays SCR or SCRs are being replaced by very good other power devices like insulated gate bipolar transistors. And then if you can recollect in the first session and second session, in fact, not the first session, I showed you a module which had 4 devices which were inbuilt inside modules. So such devices have actually replaced the main workhorse of the thyristor family, which is the SCR. However, the fundamentals that govern the behavior of SCR, they are actually very critical and important. Only when you understand the fundamentals, you can actually think about other devices. In fact, people have developed other devices based on the advantageous features of SCR, by retaining the advantageous features of SCR while overcoming the few drawbacks of SCRs. So that is what people have already done. Therefore, SCR is a very important power device. You can't skip SCR and then complete the power electronic course. So that is very important. On that note, I'll start sharing my screen and then I'll draw the characteristics, draw the structure, and then we'll start discussing today's session. Today's session will be on SCR, the structure, operation, and VI characteristics. This is what we will be discussing today. All right. Now we had discussed 2 power devices so far. We started off by looking at the power diode. So power diode happens to be a minority carrier uncontrollable device. Minority carrier uncontrollable device. Now the next power device that we had come across was 1 minute. Next power device was the power BJT. So this is correct. Current controllable minority carrier power device. So why should we need another minority carrier current controllable device when we already have power BJT? The answer is the voltage blocking capability, voltage rating of power BJT is less. Number one. Number two, BJT does not have reverse voltage blocking capability. In fact, none of the power devices they have got reverse blocking. Diode has got reverse blocking, whereas the other devices, namely BJT, MOSFET and IGBT, all the three devices, they have only forward blocking. They can block only forward voltages. They cannot block reverse voltages. Only SCR has got reverse blocking capability. So we want a device which has got good forward blocking voltage level and good good reverse blocking voltage capability. Therefore, we need this SCR. However, we should understand that power SCR or thyristor is also a current controlled minority carrier power device. Fine. I will write these points. It may take 1 or 2 minutes. In the meantime, you try to see whether you have some doubts. If you have some doubts, please feel free to get your doubts clarified. In the meantime, I will note down or I will list down certain things that I had mentioned so far. Power SCR. Simply SCR is enough. SCR represents silicon controlled rectifier. This is the head of the thyristor family. Also called as thyristor. The device is current controlled minority carrier power device. And if you want to define an SCR, it is a 3-terminal. Probably you can start from layers as well. It is a 4-layered 3-terminal power device. If you want to further quantify and make the definition perfect, you can add these points as well. It is a 4-layered 3-terminal minority carrier current controlled power device. Perfect definition of an SCR. All right. Now, what are the features of SCR? There is one more point that I need to write. I will write that as well. It has got both forward and reverse voltage blocking capability. So these are some main features of the thyristor. Okay. Now, so I will now start with the structure and other details. Now the symbol for SCR, I am not too sure whether you know, therefore I will draw that. Symbol is this. We represent the SCR like this. The terminals are anode, cathode and gate. Where A is the anode. These are well-known things. Still, I am just noting them down so that you don't get any confusion. Because after undergoing one full course on power electronics, if you don't know the terminals of SCR, then it will be pathetic to say the least. I don't want such a scenario. It is for everybody. Don't take things lightly, because I have seen many finally students finding it difficult to tell the terminals of SCR. So kindly don't or draw the symbol of SCR. So don't neglect. Incidentally, the symbol for BJT is this. I have drawn that. I know that. Still, I will draw once again. Collector, emitter, and base. This is NPN BJT transistor. Diode, I don't need to draw. I'm not belittling you, but additional clarity. That's all. I'm not cathode. Fine. Now, how does the SCR work, or what are the special features of this SCR? What makes it special? Those things we will discuss. Now, the speciality lies in the structure of SCR. So that we need to understand first. Structure of SCR. Obviously, there will be some layers of certain width, certain doping levels. So I will draw the structure alone, generic 4-layer structure, and then I will denote by the side the text that you need to refer. So kindly refer the textbook. So structure of SCR, as I had mentioned earlier, it has got 4 layers, and we name those 4 layers as PN. That's all. So this forms the structure of an SCR, 4-layered 3-terminal device. Of course, there are 3 junctions also. You can add that also. 4-layered 3-terminal, 3-junction. You can add that also. I will erase this now, and then I will include here itself. No need to erase. 4-layered 3-terminal, 3-junction power device. Make it more clear or clearer as you learn more. That's all. Now, the structure has got 4 layers, where P1 and N2, they serve as the anode and cathode respectively. P1 serves as the anode. P2 serves as the gate terminal. Right. Now, this is where I want you to refer. Refer Nedmohan book, chapter 23, for details about layer doping level and thickness. All right. So you need to refer to Nedmohan textbook. E-copy is available. Fine. Now, I said it is the head of the family of all power devices. Therefore, obviously N1 layer or N minus layer, that drift layer will be very, very thick because it needs to block large voltages. So that will be very, very thick in size. N minus or N1 layer. You can refer to textbook for additional clarity. Now, let us try to understand the operating principle. For that, there are actually 2 mechanisms, 2 ways of understanding rather. One is going to be what is happening inside the device, which means you discuss in terms of electrons, holes, and charge carriers. That is one way of understanding. The other understanding is you try to visualize the 4-layer PNPN structure as 2 BJTs which are connected back to back, one PNP and one NPN. For instance, for ease of understanding, let me try to just demarcate this. So you now have 2 structures. One is P1, N1, P2. That forms one BJT, PNP transistor. Another one is N1, P2, N2. That forms the other BJT, NPN transistor. So you can actually visualize the SCR as two transistors, and then you can understand its operating principle. So that is very famously known as two transistor analogy of an SCR. That is the other way of understanding. One way, as I mentioned, is by understanding the physics of device operation, what happens inside the device. The moment you apply a positive gate pulse, what happens to electrons, where will they go, and how does the turn on process occurs. That is one way. Other one is two transistor analogy. For ease of understanding, I will use this two transistor analogy as of now. The physics of operation also I will tell towards the end of the session. It shouldn't take more than 3 minutes, but you need to be attentive if you want to understand that. So next, let me take the two transistor analogy. This is the operating principle. This is how the SCR works. So we need to have two SCRs. First, I'll start from the top, PNP device. So anode, okay, so this is the PNP device. Then comes the NPN device. I want this to be straight. Okay. And then the NPN structure, NPN device. Cathode. Gate. That's all. Fine. So this is the two transistor model or two transistor analogy of an SCR. Firstly, you have, I will now name this as transistor T1 and transistor T2. Is going to be comprised of, it is a PNP transistor. So P1, N1, P2 layers. Whereas transistor T2 is an NPN configuration. This will be comprised of N1, P2, N2 layers. Right. I will now draw the PNPN structure towards the right so that you can correlate how this layer is obtained or how this configuration is obtained. P1, N1, P2, N2. This is just a repetition, obviously for additional clarity. Anode, cathode, gate. Now the partition or the split up happens here. This yellow color. Okay, so first is P1, N1, P2. That is this anode. I'm highlight here. So this transistor P1, N1, P2, P1, N1, P2. If you have a hand, okay. So P1, N1, P2. That forms this first PNP transistor. Next one is N1, P2, N2. That is here. N1, P2. And then you can see how the layers are tied and how they are interconnected. That's all. So this should make it clear. Hereafter, let us try to understand the process that is going to happen. There will be a positive chain reaction, positive feedback mechanism, which makes the SCR to conduct even after the gate pulse is removed. In fact, I would now like to recollect what we had discussed in the last week lab. When we gave the gate pulse for the SCR, we had given the pulse width as only 10%. And then when I was explaining that gate pulse, or the reason why the pulse width is need to be only small, I told that SCR needs only a very small pulse width. Once the SCR is turned on, gate pulse can be removed. That was the justification that I gave during the lab session. in simulation. Today we will understand what is happening inside the SCR. Why only a small gate pulse is sufficient. The reason is there will be a positive feedback that is occurring. We will try to understand that. So the first step that happens is a positive gate pulse of sufficient amplitude and time duration. Okay, before that, of course, anode to cathode must be forward biased. I didn't mention that because that is a default statement. So now we are discussing the turn on process. That also I will write. Turn on of SCR. So the first step obviously is anode to cathode must be forward biased. First thing. Second step would be you give a positive gate pulse of sufficient amplitude and time duration. I will tell the reason for the sufficient, for the meaning, or for I will tell the reason for the stress that is placed on this term, sufficient amplitude and time duration. Now, what is going to be sufficient? How do you quantify that? The answer lies in the transistor operation. So when you look at the N1, P2, N2 transistor, you have the gate here. Fine. So when anode to cathode is forward biased, which means the junction J1, J2, J3, if you name the junctions as, I will name them here, J1, J2, J3. J3 and J1 will be forward biased, J2 is going to be reverse biased if you don't do anything to the gate. Now, the moment we apply a gate pulse, positive gate pulse, J2 will also be forward biased. That is why we tell positive gate pulse, because J2 must also be forward biased for conduction to start. That is the reason for saying positive gate pulse. Next, sufficient amplitude, we will try to find out. If you look into this N1, P2, N2 transistor, for turning on this transistor T2, the base, that is the gate terminal, forms the base of this transistor T2. So for turning on T2, the base applied to the N1, P2, N2 transistor T2, that must be of reasonable amplitude. That reasonable amplitude is what is called as, is what is termed as sufficient amplitude. Because if you don't give enough amplitude, there won't be enough charge carriers. Now let us try to find out what is called as time duration. Now, if you don't apply that positive amplitude for a reasonably longer duration of time, there will be recombination which is going to happen, and the charge carriers that are injected, they will actually be recombined and conduction will not start. So the SCR is still not going to conduct. That is why we tell sufficient amplitude and the time duration. Okay. To put in simple terms, for turning on the transistor T2, the base current, which is the gate current, should be of enough amplitude and of enough duration. That's all. You understand this way. That should be enough. Okay. Now, the moment sufficient amplitude and time duration is, gate pulse of sufficient amplitude and time duration is provided, T2 starts conducting. What is T2? The BJT T2 or the N2 P2 transistor starts conducting. So when transistor T2 starts conducting, collector current IC2 starts to flow. All right. Now what is collector current? We will mark here. See, this is going to be the base current IB2. This is going to be the emitter current IE2. This will be the collector current IC2. Similarly, This current is going to be IB1. This is emitter IE1. This is collector IC1. Fine. So when IC2 begins to flow, IC2 is going to flow in this direction. This is IC2. That means IB1 also starts flowing because IB1 and IC2, they are one and the same. So when IC2 begins to flow, it means IB1 also begins to flow. Now when IB1 begins to flow, already anode is forward biased, therefore transistor T1 will be turned on. So when IB1 begins to flow, this will causes T1 to conduct, which means it is going to be turned on. Now when T1 turns on, IE1 flows and it will make IC1 also to flow. IE1 is here. IE1 is this. Sorry, I will erase this and write this neatly. When IC1 begins to flow, IC1 is same as IB2. Okay, so this means since IB2 is same as IC1, magnitude of IB2 actually increases. Now when IB2 increases, transistor T2 will be further into conduction, which means, so this means IC2 increases further. This is actually chain reaction. So this causes positive feedback. Now, because of this positive feedback or chain reaction, even when you remove the gate pulse, the SCR will still continue to turn on to conduct. Resultantly, SCR continues to conduct. Resultantly, SCR continues to conduct even after removing gate pulse. So this completes the turn on mechanism. Any doubt? So this completes the turn on process, and the way the SCR is going to be triggered by applying a very small positive gate pulse of sufficient amplitude and time duration. I will end by saying one point. This time duration, you can understand that to be time taken for this positive chain reaction to set in. You can understand that way also. That's all from my end for today.